Okay, ignore the email from my neighbor here. Section 1.3 is on composite functions. And remember last time we were talking about different ways to combine functions? We looked at how you get the sum of two functions, the difference, the product, and the quotient of two functions. Well, composite functions are another way that you can combine functions. And basically, the way a composite function works is you take two functions. You can actually take more than two as well, as we'll see. But let's just talk about two for a second. You take two functions, you find the output of one function, and then you use that as the input for the next function, or for the second function. So, little sketch here to kind of explain this. Let's say you have two functions. Remember, a function's like a machine or a rule. So let's say you have two machines, two functions. One, let's call it f, and the other one we'll call g. Okay, so here's our two machines or our two rules. And these are awesome machines because what f does is you throw a number into f, and what it does to the number that you throw in is it adds 1 to it. So you throw in an x and it adds 1 to x, and then you get an output. And for g, what that one does is you throw an input into it and it multiplies it by 3. Okay, so for example, if I was to throw 7 into here, what would come out is 8. If I was to throw 20 into this first machine, what would come out is 21. If I was to throw 7 into this machine, what would come out is 21. If I was to throw 20 into this machine, what would come out is 60. Make sense? Okay, well, you've talked about those before. Now what we're going to do is we're going to combine those two functions. Let's get rid of all that. And so the way you can kind of think of this is you kind of have you're going to put one of the machines inside the other machine. So let's take our F machine. This is the F. And let's put the G machine inside. This is G in here. So now what happens when you throw a number into the machine? It first of all goes into the inside machine, and that inside machine spits out a number. But before we see what spits out, the F machine is going to work on it too. Is this getting too abstract? So remember, the G is 3x. That's the rule for the G machine. And the F machine, or the F function, is x plus 1. So let's see what happens when I throw 6 in here. I throw 6 in here. Here's the number 6. I throw it into the machine. It falls all the way to the inside machine. What's the inside machine do? It goes 3 times 6 and it spits out 18. But it doesn't spit it all the way out. It just spits it out to here. Now the second, the bigger machine, the F works on it. What's it do to it? It adds 1. So what gets spat out here is 19. Make sense? You have two machines or two functions working on the input. So let's see, if I put negative 2 in here. Negative 2 goes into the inner machine. 3 times negative 2 is negative 6. That gets spat out to here. But the output of that first machine, or the first function, is used as the input of the second machine. So now you have negative 6 plus 1, you get negative 5. Okay, here's another very important fact. Order matters often with composite functions. So for example, what if I started by putting the G machine here and the F machine inside of that? So I've done the opposite, right? So what I have on the inside machine is x plus 1, and what I have on the outer machine is 3x this time. So remember, when I threw 6 into this composite function, I got 19 coming out. Let's see what happens when I throw 6 into this composite machine or composite function. So I throw 6 into the machine, it goes right to the inner machine. I get 6 plus 1, and what gets spat out is 7. But it gets spat out to the next function. This output is now used as the input of the next function. 3 times 7 is 21. So in this composite function, 6 is thrown in, 19 comes out. In this composite function, 6 thrown in, 21 comes out. Okay, that's the basic idea here. There's different ways you can represent this. Two different ways, basically. If I wanted to show a composite function, I could write it like this, or I could write it like this, and that's an actual little circle there. It's not an O, and it's also not a dot for times. It's a little circle. There's a whole bunch of different ways you can call this. The way I usually call it, so if it was written like this, I usually call that G of f of x. That's usually what I'll say. Other ways you could say it is G at f at x. Another way you could say it is G composed with x. And if you're talking about, I'll put quotations, those represent That's how you say it, right? And if you're talking about this last case down here, I don't know, I'll put it in a different color for some reason. If you're talking about this one, you can even say G circle F. You can actually say that. I don't think I've ever said that in my life, but you can say G circle F. I'll try to work that in a little bit this year. All right, so let's try this. It says f of x equals x squared and g of x equals 3x plus 2. Then what's f of g of what's f of g of 3? Okay, so what you should do here, always do, is you want to always start, so this is important, put a star there, always start with the last function. So what I mean by that is you have f, there's the f function, here's the g function. The g function came last. So you want to start with the g function. So the first thing you want to figure out is, what's this amount? What's g3? G of 3. So we're going to plug 3 into the x's in the g function, right? So we're going to have 3 times 3 plus 2. That equals 9 plus 2 equals 11. Now you take that output of that function is now used as the input of the next function. So now what we want to find is f of, not of 3, f of 11. That's our new input number. So what does that equal? Well, we plug 11 in there. 11 squared equals 121. That's our answer. Okay, the next one looks almost exactly the same. You see everything's the same here, except at the very end it says f of g of 3, and this one it says f of g of x. So you can't be substituting x into these things. So what you have to actually do is substitute the entire function. So what I'm talking about here is you start with that last function, the g of x. What's g of x equal to? G of x is equal to 3x plus 2, and you're going to substitute that whole amount, that 3x plus 2, you're going to substitute that into wherever you see x, and it might show up more than one spot. Here it only shows up once, there's only one x. But if you had x squared plus x, you'd have to substitute this whole amount in twice. You substitute that whole amount in to wherever you see x in the first function. So basically what you get is f of g of x. You see how basically the difference between what's written here and what's written here. What's different is instead of x, it says g of x. So what that means is wherever you see x, you're going to substitute in g of x. And what's g of x equal? It equals 3x plus 2. So you're going to plug in 3x plus 2 wherever you see x. Alright, let's try that. So I see x right here. So I'm not going to write x. I'm going to write 3x plus 2 because that's how much g of x is. And then what do we do to the x? We square it. So we're going to square all that. Okay. 3x plus 2 squared is the same as 3x plus 2 times 3x plus 2. If we multiply that by mountains and valleys, 3x times 3x equals 9x squared. Let's do these next two in one step. 3x times 2 is 6x, and 2 times 3x is 6x. Add the 6x and the 6x together, you get 12x. And 2 times 2 is 4. Okay, the nice thing about this value here is this is now like a new function that we can be used to always evaluate what f of g of x is for any number. So remember up here we figured out what f of g of 3 is, and we figured it out quite quickly. Once we have this value here, we can use that to figure out any amount we want. So let's figure out how much f of g of, whoops, I didn't write that correctly. Let's use this to figure out how much f of g of 3 is. Now we know how much f of g of 3 is. I'm forgetting some brackets here. No, I got that. Okay, good. We know how much f of g of 3 is. We already found it's 121, but let's prove it to ourselves. This here, this amount right here, is what f of g of x is. If we want to know what f of g of 3 is, we're going to plug 3 into all the x's. So 9, 3 squared, plus 12 times 3 plus 4. Don't do 9 times 3. 3 squared is 9, times 9 is 81. Plus 12 times 3 is 36, plus 4. Well, 36 plus 4 is 40, and 81 plus 40 is 121, and that's exactly what we got right there. Okay, so that's useful. If we wanted to know what f of g of 7 is, you could just plug 7 in here, both of those x's. All right, the domain. Domain remembers all the possible x values, and when you're talking about composite functions, the domain cannot be more than the domain of g. if it's in this way, if it's f of g of x, it can't be more than the domain of g. It can't be more than the inner, or I guess the last function. It can't be more than the last function. Let me show. I'll do some examples here, and we'll see what I'm talking about. Okay, so here we go. Here's some questions. Some people call this fog too. You're not really supposed to, but so here's f circle g, or f of g of x, and we want to figure out what f circle g of x is for if f of x equals root x minus 3 and gx equals x squared plus 2. So remember, we start with the last function, g of x. And in this case, there's no value here, so we have to plug the whole function in. We have to plug this whole x squared plus 2 into wherever we see x in the first function. So we're going to put that whole amount, x squared plus 2, right there. So we end up with the square root of, don't write x, write x squared plus 2 instead. I'll put it in brackets. And then I have a minus 3. Can we simplify that? Yeah, we can. We get the square root of x squared minus 1. Okay, that's the answer right there. Now, we want to talk about the domain. So what's the domain of this? Okay, there's two places you have to look to figure out the domain. One, you have to look at the answer you have right here. Well, there's definitely some restrictions on the domain when we have a radical sign with an even, in this case 2, index. What do we know has to be true about x squared minus 1? X squared minus 1 has to be positive or 0. It has to be greater than or equal to 0. I'm going to come back and solve that in a second. The other place you have to look at is the second function here, the g. So you have to look back here. Is there any restriction on the domain here? Is there anything that x can equal? No, x can equal anything in this case. So this doesn't make any difference. Okay, but you do have to check that out, because sometimes it will make a difference, like in this question down here you're going to see. Okay, back to here. How do we figure out when does x squared minus 1, when is that greater than or equal to 0? Well, we did this last year. This is quadratic inequalities. We start by temporarily making this equal to 0. And we're going to factor. This is the difference of squares, so you get x plus 1, x minus 1 equals 0. Get our roots. What would make this equal 0? Negative 1. What would make this equal 0? 1. What do we do with those two numbers? We put them on a number line. Negative 1, 1. What kind of dots should we put? We should put solid dots because it's greater than or equal. And then test a point. Let's try 0. That's the easiest one to try. So 0 take away 1 is greater than or equal to 0. Is that true? 0 take away 1 is negative 1. Is negative 1 greater than 0? No, it's not. So 0 didn't work. This area didn't work. And since we're talking about quadratics, you don't even have to check any more of them. We know that this one must work, and we know that this one must work. This is the only places where it can work. So our domain is x is less than or equal to negative 1, or x is greater than or equal to positive 1. Okay, next question. We're using the same two functions. Let me clean this up a bit here. Same two functions, but this time we're doing g of f of x, or g circle f of x. So that means that this time we start with the second function, the f, this amount, and we're plugging that amount into wherever we see x in this function. So what we end up with is, I see an x there, don't put x, put this instead. So I put root x minus 3. What are we doing to that x? We're squaring it, and then we're adding 2. Okay, root x minus 3 squared is the same as just x minus 3 plus 2, so you get x minus 1. That's your answer. Again, we have to look at the domain. Two places you have to look. You have to look at your answer here. Is there any restriction on the domain here? No, it can be anything, right? Doesn't matter what number x is. We also have to look at this function f. So we look back at f. Can x be anything here? No way. X cannot be, this x minus 3 has to be greater than or equal to 0. This is not quadratic, so these are easy to simplify or to solve. Just move the 3 over. X is greater than or equal to 3. So the domain is that x is greater than or equal to 3. Doesn't work for x values lower than 3. Okay, GOG x, g of x. What does that mean? That means, so again, let me clean this up a bit. That means you are going to take the g function and plug it into wherever you see x in the g function. Gets a little confusing here. So you're going to take this amount, the x squared plus 2, and plug it into the same function wherever you see x. A little confusing, but let's do it. So I see x squared, x, but I'm not going to write x. I'm going to write x squared plus 2. Now, what are we doing to that x? We're squaring it, and then we're adding 2. You might need to rerun the video a couple times to really get this. I'm taking this amount, x squared plus 2, and I'm putting that amount wherever I see x in this function. Okay? I understand if your head's spinning a little bit. Alright, x squared plus 2, so that's the same as x squared plus 2 times x squared plus 2, and then we have to add another plus 2 right here at the end. Mountains and valleys, x squared times x squared is x to the 4th, x squared times 2 is 2x squared, and 2 times x squared is also 2x squared, so I end up with 4x squared. 2 times 2 is 4, but I'm adding another 2, so I get plus 6. Domain. Okay, if we look at what we've just found as our answer, is there anything x can't be? No, x can be anything there, it doesn't matter. We also need to look at the second one, which is g. Is there anything x can't be here? No, it can be anything. So domain is all real numbers. It doesn't matter what value x is. Okay, last question on this page is g of f of 19. So, the nice thing about this one is we have the input number here. So there's no point, I wouldn't suggest you take all of f and plug it into the x and then take all the amount and put it into, it's going to be a crazy answer. If you have the number, it's really nice because you can actually start with this last function, the f, and figure out what is f of 19. So f of 19, f is root x minus 3, so we just do 19 minus 3. We're replacing the x with the 19. That's the same as the root of 16, which is equal to 4. Okay, that's my new, even though it's an output of this function, it becomes the input of the next function. What's our next function? Another f. So we have to find f again, but this time for 4. So this time it equals 4 take away, the square root of 4 take away 3, which is the square root of 1, which is 1. That's my output of that function. It now becomes the input of the next function, which is g. So we have to find what g of 1 is. Okay, g is x squared, so we put 1 squared plus 2. 1 squared is 1 plus 2 is 3. Our answer is 3. Alright, moving on. Decomposing a composite function. So this is kind of like going backwards. We start with the composite function. You have to find two functions that when you compose them, you could get this. Now there's actually there's like more than one answer for this. But basically what you want to do is you want to look for the inside, like an inside function or last function. Like you should see something that's inside. If you take a look at this whole function here, you should see something or some things that kind of are smaller parts of the bigger function, of the whole function. Again, probably an example is going to help you here. So what I see is that x minus 2 kind of recurs here and it's kind of inside the whole function. So make that your last function. Make that your gx. Gx equals x minus 2. If gx equals x minus 2, what could that make fx so we end up with this? Well, instead of x minus 2, let's call that x squared plus, we have to write x minus 2 again here, so it must be another x plus 1. I don't know, it's a hard thing to explain, kind of, but hopefully by seeing a couple examples you get the idea. Do you see that if it was f of g of x, we'd be plugging this amount, this x minus 2, wherever we see x in this one. So we'd be plugging in there and we'd be plugging in there. So you'd get x minus 2 squared, yes, just like this, plus x minus 2, yes, there it is, plus 1. So it works. You got to try to find that inside function. Okay, the next one. What is the inside function here? We have the square root of x cubed plus 1. Well, the inside function's the x cubed plus 1. That's the part that's like within the other part of the function. It's the smaller part of the function. What should we call that one? Well, the last function, the inside function, is the f. So this would be my f of x. Remember, order is very important here. What does that make g of x? Well, basically what we do to the x cubed plus 1 is we take the square root of it, so we'll put square root of x. Again, when you see the answer, I think it kind of makes sense, but I know it can be kind of hard to figure out what the answer is. But again, if I was to take f of x, x cubed plus 1, and plug it into g wherever I see x, I would be putting this amount right there. I'd be left with the square root of x plus 1, and that's exactly what we have right there. Okay, last question. we want to use a graph to do this. So let's call this one up here, the blue one, we'll call that f. This is my function f, and the black one is my function g. And again, it's hard for me to draw these in Word, so I tried to make pretty points. Let's pretend that a lot of the points I use here are pretty points, okay, to the best of our ability. So here's what you do. You start with the inside function, so we want to figure out what's g of 2. In other words, for an input value, so we're looking at the g function, the black function, for an input value of 2, input's x, right? So for an x value of 2, that's right here, what's the output value on the g function? What's the y value of the g function? Well, that's right here. What point is that? I know it may not be perfect, but let's pretty darn close to -3. So this is -3. That's what g of 2 is. Now we want to know what f of g of 2 is. In other words, this output value here becomes the input of f. So we want to know what's f of -3. So again, for an x value or an input value of -3, 1, 2, 3, what's the output value? But this time we're looking at the f function, the blue one. So what's the f value, the output value, sorry, when the x is -3, the y value is basically 6. So our answer in this case is 6. F of g of 2 equals 6. Two more quick ones. Okay, we start with the inside function, so we're doing f of 0. So for an x value of 0, what's my f function's output? 4. So f of 0 equals 4. That now becomes my input for the other function. So now we have to figure out what's g4. So we go to 4, and did I do something wrong? F of 0 equals 4, and then 4, and basically equals 0. I got it wrong on my answer key. Bad. Alright, and the last one, f of f, or f circle f, of -5. So the first thing you want to do, sorry, let me write in the answer here, 0. I'm doubting myself now, I'll check it later. The first thing you want to do is figure out what f of -5 is. So for an input value of -5, what is the output value for the f one, that's the blue one? It looks like it is 7. And then I'm putting that output value now becomes the input value of the next function, but look at, we're using f again. So now you put it into the f function, f of 7, so for an input value of 7, we're using the f1 again, which is the blue one. What's the output value? Well, this one doesn't look very much like a pretty point. Let's say it's a halfway, so it looks like a -5.5, I would say. So the answer is -5.5. That's it. Composite functions are now done.